Okay, today we will talk about step functions 6.3. So if you remember last time, we solved an example of a differential equation, second order, by using two methods. The first one, the method we learned in chapter 4, the characteristic equation and the undetermined coefficient method. And then also we solved the same question by using the Laplace transform. And we saw that actually the first method we use is faster. But now today, actually we will learn why we are learning Laplace transform. Because as I said last time, when the forcing function, the function which makes your equation non-homogeneous is not continuous, it is discontinuous, but it is piecewise continuous, and we will see that Laplace transform is faster than the other method. All right, so what I'm talking about is the following. So let's say that we are given an higher order constant coefficient linear differential equation, and which is not homogeneous because of G. And if G is a continuous function, actually you can use the older methods to find a particular solution. Variational parameters or undetermined coefficient method, and they're actually better than Laplace transform. But if G is a discontinuous function, so if this function, I'm going to call this function as the forcing function, just imitating that. If you remember the mechanical vibration, so when there's a function on the other side, we call that forcing function. So just I'm using the same terminology. If there is a function on the side, I'm going to call it the forcing function. If this forcing function is not continuous, but if it is piecewise continuous, means if it has some jumps or holes, then we will see that Laplace transform is faster. But first of all, we should learn how to write the Laplace transform of discontinuous functions. Okay? So then for this now, we will start with the step function. So what is the step function? So we'll use the following notation, UCT. I'm going to define this function first. Okay, so from this we will understand U is the unit step, unit. So C means, everything's happening at C. So when T is less than C, this function is going to be 0. And when T is bigger or equal to C, then this function is going to be 1. So this will be the first example of a discontinuous function. And actually, we will use this one to write our discontinuous, piecewise continuous functions. All right. Now, if you look at this, how is the graph? Now, there is the C here, which is the important thing for the using step function. And until C, this function comes as 0. So until this, it comes 0, comes 0. Remember, our signals are always, or our functions are always starting from 0. That's the beginning. Okay, so if you want, you can write 0 here. But when it comes to C, then after that, it continues as 1. Okay. So this is filled. Actually, it doesn't matter which one is filled because the integral will not notice it. So it will continue this way, and it is 1. So I want to think them as like signals. So your function, if you look at your signal, or it starts as a 0, and then when the time comes at C, then it continues at as 1 forever. So this is the unit step function. Okay, so this is the unit step function at C. Why unit? Because our signal is like continuing as 1. Okay. And now we will play with this function, and if you take the following function, and let's try to understand this. If I take UCT minus U dt, where I'm assuming that here d is bigger than c. Okay. Now let's try to understand this function. And so what does it say? You have to add two functions like this. And if you write these things in the following way, so between 0 and c, it is 0. When t is bigger than c, it is 1, minus 0 when it is between 0 and d, and when t is bigger than d, it is 1. So I'm basically subtracting these two-step functions. And then what do we see now? As you see now here, there are two important numbers, c and d. And if you think like the first signal comes as 0 until c, and then it continues as 1 after c. So this comes as 0 until d, and then after d it continues as 1. So then, what happens until c? Because c is less than d. So when we have between, so when it is, when time is less than c, when time is less than c, then this is 0. So since c is less than d, this is also 0. We see that it is 0. Now, when time is between c and d, because c is less than d, now the first function or the first signal became now 1, but the second signal is still 0. So we have 1 minus 0, so we have 1. In the previous case, I mean, we are basically subtracting 0 minus 0. Now, what happens? So now we reach d. So when you pass d now, so you automatically pass c. So when you pass now c, and so d, I'm sorry, then what do we understand? Since you are automatically after c, then we have 1 here, and also we have 1 here. When you subtract them, you get 0. So if you draw this now, so this is c, this is d. So now our signal comes at 0. And then it becomes 1. Which is filled. It continues as 1. When you come d, now it becomes 0 and it continues as 0. So now you can think like this signal as coming as 0 as a bump, which becomes 1, and then it becomes 0 again and continues as 0 forever. All right. Then, okay, so these are just two step functions I drew. UCT, our basic unit step function, and then now I took two step function and I subtracted them. And then from that, I got this following two graphs. All right. Now, why do I care about these unit step functions? Now, I will use this kind of functions, unit step functions, to write any given discontinuous or piecewise continuous function. And just notify, I want to notice the following. I mean, so the UC minus UD, so signal comes as 0, becomes 1, and then becomes 0. And everything is happening between the time c and d. And so it is 0, 1 there, the rest is automatically 0. All right. Now, let's take an example of a piecewise defined function. All right. So let's look at the following example. Okay. So when time is less than 2, it is 0. When time is between 2 and 4, it is 2. When time is between 4 and 5, it is 5. And when time is bigger than 5, it is 0. Now let's look at the following function. So this is a locally constant function. And if you look at its graph, just to see, so we have 2, 3, 4, 5. And so the important numbers are 2, 4, and 5. So let me just indicate those. So between 0 and 2, it is 0. And between 2 and 4, it is 2. And between 4 and 5, it is 5. And after 5, it is 0. This is what we have. So, as we can see, like this is a piecewisely defined function. It is discontinuous at 2, 4, and 5. Now, if you think like this as a signal, your signal starts at 0, it becomes 2, and then it becomes 5, and then after that, it dies after 5. So it becomes 0 again. But now, this thing can be written in the following way. I can just consider this thing as the following sum of two signals, actually. There is a bump here, and there is another bump here. Other than these two bumps, then this function is completely 0. So if I take the following functions, so I'm just doing a graphical addition now. So this is 2 and 4. Take this function plus the following function, and which is 0 until 4. Then it is 5. And then after that, it is 0. Okay, so if you add these two functions, actually you get the 1. Because what is happening between 0 and 2, this is 0, this is 0, 0 plus 0 is 0. Okay, and between now 2 and 4, this is 0, this is 2, 2 plus 0 is 2. Between 4 and 5, this is 5. But this is 0, because if you write here 5, then 0 plus 5 is 5. So basically, I get these things. But now, if you look at this, according to the previous example, if I take u2 minus u4, if you look at this function, this thing says that until 2, it is 0. Between 2 and 4, it is 1. And then after 4, it is 0. So if I write this thing, then this is a signal which is 1 between 2 and 4, and then the rest is completely 0. But my signal is not 1, my signal is 2, so if I multiply this function with 2, I just make my signal not 1, but 2. So that means that this signal can be written as this way, u2 minus u4 times 2. So this is just telling you everything is happening between 2 and 4, the rest is completely 0. Between 2 and 4, this function is 1, and I double it. So I get this one. So when you come to this, now this is happening between 4 and 5, as you saw in the previous case, between, if you write u4 minus u5, then you get that. This is a signal which is 1 between 4 and 5. The rest is completely 0. But now this signal is not 1, it is 5. So if you just multiply with 5, you exactly get this signal, or this function. So now if you write them, so what do I have here? I have 2 times u2 or you can write u2 times 2. So minus 2 times u4. So we have 5 times u4 here, 5 times u4, 2 times u4 subtracted, so we have plus 3 u4, and eventually we have minus 5 times u5. So what happened here? I was able to express my function f, in terms of unit step functions with some coefficients. So this was the example, and which shows us actually, starting from now on, you can write your piecewise and continuous functions in terms of step functions. Let's do one more example. Your signal doesn't have to be constant. It can be any signal actually. All right? All right, so f of t is the following signal. When t is less than 1, our signal is 2. So when t is between 1 and 2, it is t minus 1. When t is between 2 and 3, it is t minus 2. When t is bigger than 3, so our signal is 3. This is what we have. So if you draw the signal, actually, or I'm calling them signals, so just get used to that. So between less than 1, I know our signals are always starting from 0, so this is 1, 2, 3. So between 0 and 1, it is constant as 2. Between 1 and 2, it's the function t minus 1. So at 1, it is 0. At 2, it is 1. So like this. It doesn't look good, so let me just, so this is 1, 2 is somewhere here. Okay, so, and between 2 and 3, it's t minus 2, so when you plug in 2, you get 0. When you plug in 3, you get 1. So it's like this. And after 3, it is 3. Continues as 3. Okay. So this is the signal now we have, or f function. So as you see now here, and for this signal, you can think like there is one signal here, the rest is completely zero. There is another signal here, the rest is completely zero. Another part here, the rest is completely zero. And this part, the rest is completely zero. So you can divide this thing into 4 parts. This part, this part, this part, and this part. So when you add 4 signals, then you can get this signal now. So what is all about? It's all about where the bumps are. There is a bump here. Bump means like non-zero part. There's another bump here, non-zero. There's another bump here, non-zero. There's another part here, non-zero. Now let's write it from this above one. If you look at between 0 and 1. So this can be written as U0 minus U1. Okay, so if you look at this, this just gives us a signal which is 1 between 0 and 1. The rest is completely 0. So I just care about the first bump. So the rest will be 0 for me now. But it's not 1, it is 2. So I double it. Now, let's count this portion. Now, in this case, we have U1t minus U2t. Okay, so if I write this way, it's just 1 between 1 and 2. The rest is 0. But my signal is not 1. My signal is t minus 1 because it's the function. So I just multiply with t minus 1. Okay. So when you multiply with t minus 1, so it says that everything is happening between 1 and 2. Other than 1 and 2, this function gives you 0. So whatever you write here, it multiplies with 0. So it's all about between 1 and 2. So between 1 and 2, it's t minus 1, so we get this. Then plus, for this one, things are happening between 2 and 3. And between 2 and 3, my signal is at 1, because this gives me 1. I have to multiply this with t minus 2. So it says that this part just cares about between 2 and 3. It is 1 there, 1 times t minus 2 is t minus 2. The rest, this function gives you 0. Whatever this is, you get 0. So basically we wrote this part. And then after this, it's just U3t, because U3t says, it's 0 until 3. After that it is 1. So I multiply with 3. This thing says until 3, completely 0. After 3, it is 1. So 1, and then if you multiply with 3, you get 3. So this is the signal we were able to write by using unit step function. So if you now expand it, 2 times U0, typically, rather than writing U0, we accept it as the constant function 1, because we know that t starts from 0. There is nothing before it. So rather than writing U0, we typically write it as constant function 1. So we have 2 times 1, which is 1. So 2 minus. Okay, now let's look at what do we have here. We have U1t here, and we have another U1t here. And here it says that t minus 1. Here it says that minus 2. So if you write now U1t, which is multiplied by t minus 1 minus 2. Now I'm adding these things. And now there's U2. So here we have t minus 1 subtracted, but t minus 2 added. So what we can do is we have t minus 2 added and t minus 1 subtracted. Okay, so that's 1 and this is subtracted. Now we have U3. And here the t minus 2 subtracted, but 3 added. So we have 3 minus t minus 2. So now this is what we get. So you can do the algebra here. So this is t minus 3. Let's write it actually. This is t minus 3. And This is now t's are canceling. We have negative, so this is plus, so we have here -1. Okay. And here we have and 5 minus t. All right, so this is what we got now. Now, I want to do the same problem. I want to do the same problem in a different way. You can do this way, or you can do this way. But I typically choose the second method, and I will follow that. But it's up to you. You can do the way I did here, or the one now I will introduce in a minute. Okay. Now, the idea is thinking your function as a signal. All right. Second way. Now, what is happening for my signal? My signal or my function starts as 2. Okay. But if I just write 2, this means that this function will continue 2 forever. But it doesn't continue as 2 forever because there's a change happening at 1. So now there's a change happening, and it's happening at 1. So to arrange this, if I want to make a change just starting from 1, then I need to use the function u1t, because u1t says my effect is only after 1. Before 1, I'm completely 0. I will not do anything because 0 plus 2 is 2. Nothing happening. So then what is that change? So your signal was coming 2. But you want to make it now t minus 1. So what should I add? What should I add to 2 to get t minus 1? So I must add t first. But to get -1, I have to subtract 3. So then what happened? Before 1, there is no effect of this. It's completely 0, so it's just 2. After 1, this is affecting, and this is affecting. So that I have to add them. After 1, t minus 3 plus 2, which is t minus 1. So now if I leave like this, it comes as 2. Starting from 1, it becomes t minus 1. But our function is not like that. So there's something happening at 2 too. So, and change is coming at 2. So I'm writing u2 here because I can control the change at 2 by using the unit step function at 2. Because before 2, this will be 0. There is no effect. After 2, I have to add this thing to this part. Okay. Now, what should I add? So between 2 and 3, it is t minus 2. But now, if you look at this part, 2, now, after 2, 2 is coming. After 2, t minus 3 is coming. So it's now t minus 1. But I want to make it now t minus 2. So it came, my signal came as t minus 1. Because if you add these things, it is t minus 1. Now I want to make it t minus 2. So I have to subtract 1 from this. So now when you add them, 2 plus 3, t minus 3 minus 1 is t minus 2. So if I leave like this, my signal will continue as 2 minus 2 forever. But it's not continuing that way. There's another change coming at 3. So now I can control it by introducing u3t. So this says that my effect is only after 3. Before that, just add these things. All right, then what should I do? After 3, your signal continues as 3. So before 3, when you add them up to t minus 3 and minus 1, you basically get t minus 2. But I want to make it 3. So first of all, I should cancel t. So now it was t minus 2 minus t, t vanished. Then I want to make it now 3. It was t minus 2, t is cancelled. To make it 3, I have to add 5 to this. So now this is what we get. So when you add them up, 2, t minus 3, minus 1, minus t plus 5, then you will get 3. So if you look at, it's the same solution. Rather than just writing and then doing some algebra, just arrange it according to your signal. So just look at where the changes are happening and then write your function accordingly. All right. All right. Now, how about their Laplace transform? To understand it, first of all, we have to find the Laplace transform of the step function. And then, how about a step function times another function? How about their Laplace transform? We should do this thing. All right. Now, Laplace transform of UCT. What is this equal to? So this is equal to, from 0 to infinity, e to the minus st times UCT dt. Okay. But now if you look at this function UCT, this is 0 before c, after c it is 1. So before c, this function is 0, 0 times anything is 0. So I don't care about the integral from 0 to c because it's completely 0 there. So this is from c to infinity, and we have e to the minus st, and after c, it's constant function 1 dt. So now if you look at this, limit as a goes to infinity from c to a e to the minus st dt. So if you write this, the entire derivative is e to the minus st over minus s from c to a. And then we take the limit as a goes to plus infinity. So this is limit as a goes to plus infinity. If you plug in a, e to the minus s times a over minus s, minus, if you plug in c here, we have e to the minus cs over minus s. So again, we care about convergence. So when do we have a convergence? Again, we have exponential. This can only converge to 0. And for that, s must be positive because a is positive already. So if they are both positive, this will go to 0. So this part will be completely 0. Since there is no a here, just this is constant with respect to the limit. So then eventually we will have this. So which is, if you do, which is e to the minus cs times 1 over s and s positive. So this is the Laplace transform of the unit step function at c. So now if you look at, now just to use the following analogy. So think like, there is a 1 here, there is a 1 here, UCT times 1, and eventually, if you look at, there's an e to the minus cs coming and times 1 over s, and we know that 1 over s is the Laplace of 1 here. Okay. Now, how about the other case? If your function is not constant 1, but if it is just a function like this, t minus 3 or t minus 2 or any other thing, then how am I going to compute the Laplace transform of the function times the unit step function. Right, now, before this, I want to do the following. We know the following property, remember, when you have a function f, if you multiply this thing with an exponential, as we did before, this is just giving you a shifting in the s domain. So this is equal to f of s minus a. What is f of capital F here? Capital F is exactly the Laplace of the small f. So it says that in the time domain, if you multiply a function or a signal with exponential, then this will result in a shifting in the s domain. Okay. How about if I shift in the time domain, what will happen in the s domain? Okay, so now how about f of t minus c, f of t minus c is Laplace transform. So if I shift in the t domain, what will happen in the s domain? Now, in a couple of minutes, you will see the relation, why I'm doing this. Okay, but now, there is one thing here, you should be careful. Let's say that this is your function f. I'm just drawing something continuous. So this is your f of t. And now when you shift it, this is c, and it's this function. Okay, so this is f of t minus c. You are shifting to the right. Okay, so then you can consider this as the following. Like this is your signal starting from 0. But then this it's the same signal, but starting at c. You can consider like there is a delay in the signal. Signal is not starting time 0, it's waiting until time c, and then it is starting. So there is a delay in the signal. So we are trying to understand if there is a delay in the signal, what happens in the s domain? What happens in the Laplace transform, under Laplace transform? Okay. But the thing is now I want to find the Laplace transform of this. Okay, I want to find the Laplace transform of this. But I can't do it because I need to integrate from 0 to infinity, and there's a gap here between 0 and c because my function is not defined there. If you just shift it to the right, there was nothing before, so when you shift it, and there's a gap here. But I want to fill that part as 0 because I want to think like it's a delay here, my signal is nothing, it is 0, and then it starts. Okay, and then it starts. So that's why I want to fill this part with 0. So nothing is happening, and then starting from time. See, it's the same signal. So it's exactly delay now. Because there was a gap. Now I fill the gap with 0. Now it's a... But it's not the same thing anymore, because now it's not the same thing. So this became actually UCT times f of t minus c. So there wasn't any definition before, but I don't care because whatever it was, when you multiply with 0, you get 0. So now it is 0 until c. After c, this is now 1. It's 1 times the original function. So it's exactly the shifted signal. So then now I can talk about the Laplace transform of this. So that's why I'm correcting my Laplace UCT times f of t minus c. So what is the Laplace transform of this? Because I have to have to fill that part. Okay, now let's talk about this Laplace transform. All right, UCT times f of t minus c. And now I know that just remember the computation for the unit step function. This product is completely zero until c. So this is going to be the integral from c to infinity. And between c and infinity, this is going to be itself because this is 1, it's itself, so this is what I have. T minus c dt. So this is what we have. Okay. So I skipped the first step. So you write from 0 to infinity, between 0 and c. This function is 0, so just we need to integrate from c to infinity. This is what we have. Now, I want to do change of variable. Let's call this t minus c as u. Then du is going to be dt. So with this now, what do we get? And we will have e to the minus st. So what is t now? T is equal to u plus c. And we have f of u du. Now, if you look at the lower bound, c minus c is 0. Now, what happens for infinity? As t goes to infinity now here, so u will also go to infinity. So this is what we have. It's the same thing, from 0 to infinity. But now it's from 0 to infinity. If you reorganize it, from 0 to infinity, e to the minus su u du. So what is left here, if you look at this, we have e to the minus cs. But e to the minus cs, c and s are constant with respect to your integration. So I can put it out. E to the minus cs here. But now, if you look at this, this is exactly the Laplace transform formula. For which function? F. And rather than using t, I'm just using u. It's the same thing, like t. So you will get the Laplace transform. So what do we get here? This is equal to e to the minus cs times f of s. So Laplace transform of the delay is just multiplication with e to the minus cs in the s domain for the Laplace of f. Okay, so this is what we have now. But so what do we learn from here? Then, if you are going to use this formula, then the shifting here and this one must match so you can use it. When f is constant, so if this function is constant, we know the answer because we know Laplace transform is linear. So then we can easily take the Laplace transform. So what I mean, like for the sake of completeness, if you look at the following examples, so first example, what is the Laplace transform of u to t times 5 So just 5, you can put it out. It's all about the Laplace of this, and its Laplace is e to the minus 2s times 1 over s. This is what we have. And now, if you look at the Laplace transform of u1t times t minus 1, okay? So this is going to be, so if there is u1t, if you look at the formula, there will be a e to the minus s in it. And now they match. There's a shifting 1 here, but what is that shifting? For which function we are shifting? Actually, our original function was t, and we are shifting 1. So if you look at now, remember, what was f, capital F here? That is the Laplace transform of the original function, not the shifted function. So here, this is my shifted function, t minus 1. What was the original one? That was t. So if you shift within one amount, this is what you get. So I have to write here Laplace transform of t. And if you remember the formula for this, so t to the 1, so we have 1 factorial divided by s to the 1 plus 1, which is s squared. So what we have. So that's the reason we are not taking the Laplace transform of this. It is only true for constants, actually. We have to look at the original function. What was the original function? We have to take the Laplace of that one. So we have to make an arrangement. So let me finish with a little bit more complicated example than this one. u2t, and how about t here? I want to find this. But now if you look at, I cannot apply the formula because it says that if you want to apply, there must be a shifting here with 2. So then I will just manipulate it. I will try to make this part look like t minus 2s in terms of t minus 2s. So I can do the following trick. So you can see, like, I will not use t's anymore here. I have to use t minus 2s. So I'm writing t minus 2. If I write this, my function became t minus 2, not t. So I'm not correcting it, 2. So I wrote the same thing, but by using t minus 2s. So then if you look at this, one, so now this function next to u2t is written in terms of t minus 2s. So like your function f is written in terms of t minus c's. Here my function t is written in terms of t minus 2s. So then now we can use the formula. This is e to the minus 2s times. So then I have to look at the original function, the non-shifted function. This is the shifted version. So if you look at the non-shifted version, so all the t minus 2s must be replaced with t back. So then if you replace this thing with t, so it's t now here, plus 2. So the original function is t plus 2. So I have to write the Laplace of that one, so which is 1 over s squared plus 2 times 1 over s. Okay. So now you can think the following way, like f of t was originally t plus 2. Then if you look at f of t minus 2, this is t minus 2 plus 2, which is t. So your shifted thing becomes t. So what original function was t plus 2. So that's the reason we have to take the Laplace of t plus 2 in this case. Okay. Now I want to stop here, and then we will continue with some more examples, and then we will use them to find a solution of initial value problems where the forcing functions, or the function which makes it not homogeneous, are piecewise continuous.